Okay. Sorry, folks at home, forgot to start the stream. This is why this is not an online class, because I cannot guarantee that I will always remember to do that. But you can see where we're at here. Replace experience 4 to 7 equals experience minus 4 if experience is greater than or equal to 4. Does that make sense?
Returning off, yes. Yes, it does.
Okay, so this is the state aversion. Making two new variables and setting them to equal to start with. Replace experience 1 to 4 if experience is less than 4 with this right here. Minus 1 gets you that. Replace the second half if experience is less than 4. Nope, that's wrong. That's not right yet. Replace if experience is less than 4. Hang on, is that right? Yeah, no, this one. Experience is less than 4. This one needs to be 0. That's why. And this is why it's good to make a little table like this to check your code against, because it gives you the logic that your code is trying to accomplish. There we go. So the first two lines deal with this section right here. If experience is less than 4, then it's minus 1 or 0. The second two lines deal with this chunk. So if experience is greater than or equal to 4, the first one is 3, and the second one is experience minus 4. Got that, I believe, is correct. And I'll show this part again since I wasn't filming when I started that. We got the Stata code over here that accomplishes this contrast for the 4 group example from section 1, and the SAS code that goes with it over here where I need to fix this one to be correct. There we go. All right, so Cole, are you good?
Yeah.
Okay. So then the differences in the slopes. Same principle as what we did for the 3-group problem. One slope minus the other. Linear combination of the two. So the only difference would be substituting the names of these variables rather than the names of these variables. So do you want to do that one too? Okay, in Stata, since we're on Stata right here, there'd be lincom. Experience 1-4. And if you do it the way that I normally do it so that everything stays as additive, it'd be like that. That gives you the difference. There we go. Or more simply, that does the same thing. It's just the difference. But one way lends itself to a more general expression that can get you about anything. SAS folks, it'd be estimate, please help me.
Yes.
And then order matters, so we'll go, gets the -1, order 7 gets the 1, semicolon. There. Where is, there it is. There we go. And if you wanted to add comments to your Stata code, by the way, that's where the little // 2 slashes, please help me. And then I'll add this one. No, really, please help me. There. How's that? Okay, so now I'm recording, so you can come back to this if you need more clarifications. Due tomorrow night. So any other questions on this? Everyone's looking at your computers. That means you're either bored or lost. Bored, I'm okay with. Lost, I'm not okay with.
I'm great now, so I don't know what the rest of y'all. I can stop looking at my.
Other questions? I'm happy to go over things, yeah. That, so the role of the // here is these are comments. So anything, let me show you what it looks like in context. So for instance, in Stata, do you see this? This is green. That indicates that it's something that the computer isn't reading, it's just a note to yourself. It's your trail of breadcrumbs as to what things mean. So in Stata, no, you do. You do have to write something. So when you write an estimate, it insists you put some words next to it to go in the label column.
I did that, but
Hmm?
I put like what it meant, not like just like.
What it meant would be an excellent choice. I was just trying to be funny. So yeah, so like right here, like what I'm asking it to create is the mean for the low group, and so I titled it low mean. Right, there's no way to do that directly in Stata, so I did it as a comment at the end of the line. And yes, I was just trying to be funny, that this is please help me. I'm sorry it wasn't funny, but I tried. Yes, ma'am.
So when you're talking about a negative slope, but we're talking about golf, so negative is actually positive, but you're still using negative like math, right?
So lower scores are better.
Yes.
So if you have a negative slope, that means your score is lower as the variable goes higher, which means the variable is helping. More of a variable leads to a lower score.
Yes.
That is good.
But would I still say it's significantly negative, even though I'm glad personally that my score is going down?
Yes.
Okay.
Significantly negative by the number line.
Okay, but then they have the other question.
Yeah, but then it's like, therefore it is helpful, or therefore it is harmful,
Okay.
where you can clarify what negative means. Yeah. Yep. And yes, so while we're on the topic of this, so I'll just take these off because this is not funny, apparently. Slope difference, right? So if you were to put my labels on your homework and then come back to them in like a year, you'd be like, "Lo, what? What the hell does this have to do anything?" So I've seen several pieces of code where people are stealing from my examples, but they don't change everything. They leave the titles or the comments the same as the old example. Don't do that to yourself. It will make no sense when you come back to it, and the whole reason that I'm forcing you to go through this process is so that you have an arsenal of things you've developed to use for your future reference. Because as cool as it sure may be to you that I can do all of this off the top of my head, it's from practice. It's not like I expect you to memorize Stata code or SAS code. And in practice, whenever I have to do something that requires more than a couple lines, I think to myself, when did I have to do this last? And I go to that folder and I steal my code and I do a bunch of find and replaces to swap out the things. So I want you guys to have that, to begin building that arsenal. So please try to remember to change titles, comments, all the things that would leave you your trail of breadcrumbs to revisit this work later on. So, no really slope difference. There we go. All right, others.
So, okay, so now that, and I hope I'm not asking for a question here. So now that there's So now that I know I have to estimate for the slope difference and I don't just actually just subtract one from the other using my calculator on my phone, the p-value changes. And so then, so when you're asking if it was worthwhile to do piecewise models, would that be in relation, I'm just basically asking for it, would that be in relation to a p-value for difference?
Yes, it would be in relation.
Okay.
So let me answer the question you didn't ask. Like, I know I shouldn't do it on my calculator. Yes, you can find the difference in the slopes if you plug the numbers in your calculator, and you will get that correct. What you won't get is the standard error for the difference, and thus the p-value. Now, there are formulas by which you could compute the standard error, but I don't want you computing anything. I want you to let the software do it. Because those formulas get more complex the more complicated the model gets, but the code never does.
So logically based, when a standard error is significant, then that means that the
P-value.
I'm
Okay.
sorry.
Yeah, back
the
up.
If the standard area, the p-value of the standard error is significant, then that means that it was significant that those two slopes were made.
Not quite. Okay, so this is a good vocabulary exercise, right? So if I take the estimate itself, like that's the value of your slope, how y changes per unit change in x, right? The standard error for that is an index of imprecision of that value, okay? So if I have the estimate divided by the standard error, what do I get? Estimate divided by standard error gives me what? T. Okay. T is what gives me P. T, remember T? It's kind of like the squatty looking normal distribution, normal but squatty. And so p-value then is the probability of finding a t that extreme if the true t were 0, if the slope were 0. So the p-value goes with the estimate and the standard error. It's like the combination of the two is what gives you the p-value. Okay. So you had the right ideas, just not quite the right words to go with it. That's cool. So then go back to my picture here, the way that I drew this, it kind of looks like these slopes are the same, right? Like I could have just done that and called it good. So if this is true, if one slope is sufficient, this number will not be different than that number.
I see.
And the p-value for the difference would say the difference is within expected territory. Now, what if more experience only helps to a point? Is that possible?
Yes.
So then, at the low end of experience, let me erase my drawings here a little bit, the magical 4 here. At the low end of experience, maybe you have a negative slope, but then at some point, like more doesn't really help. So then this number is not the same as this number, and 2 would work better than 1. So if they're different, then that means you need both of them, right?
So, this is my last question, I promise. So if I wouldn't have run for these piecewise slopes, then it would have changed the overall slope if I wouldn't have counted, if I wouldn't have broken it up.
Yeah, so let me try and make this a little...
Or wouldn't have adequately represented or whatever.
Yeah, so let's say that this is truth. Okay? The one that you would fit through this would be sort of like a smishmash of the two, right? Smishmash, that's a new word. It would be biased. That's the stats term. But wrong is the term you can use, yeah. So if it really should be these two things and you're trying to fit one line for what should be two, that one line is going to be some sort of blend of the both. So yeah. Meaning one line would not be sufficient if you really need two. Okay. And why 4? Because I wanted you to practice piecewise. I have no better reason than that. So this is a completely atheoretical model. But at some point, you may want to test something that the values like represent, say, cut points, for instance. Like if you have, say, depression scores, counseling people, or anxiety scores, after which like you're considered like problematic or in need of treatment. You might expect that higher scores mean something different after that cut point than before. That would be an example of piecewise models. I gave you an example with education, where years of education looks like this, and I screwed it up. So I watched the video back and verified that I screwed it up. So in the interest of reminding you that we are all human and that we all screw things up, so this is what it should look like. Grade 11, in my piecewise education example, was the 0 point. Make this, clear some of the stuff out of here. I wanted to have the slope before grade 11, so that's indexing the change relative to that point. I wanted a boost for graduating high school, so that goes to 1. And this shuts off. This isn't active yet. This is a 0. I had a 1 there before, and it should be a 0 because I want it to pick up after high school and index what happens after that point. Whereas this one stays at 1. So I watched it back and realized that cell was wrong. That should be a 0, not a 1. But I did code it correctly, so I just talked about it incorrectly, which is good. Because that meant less work to have to redo it. So this slope captures the change from this point, from below 11 years up to 11 years. Graduating high school captures the jump from going from 11 to 12. And then over high school captures the additional increase for people who are past 12 years of education. All right. It's already 1:17. Goodness, time flies. If you ever need to do this in your life for your research, send me an email. I'll help you figure it out. It's tricky, it really is, but it's one of the cooler things is to be able to hypothesize functional nonlinearity like this. And last but not least, section 2, which we haven't talked about, the shortest section, you don't have to make any new variables for this. Just fit a quadratic effect of enthusiasm, in which you can leave it uncentered because 0 is the mean of the scale. All right. Other questions? Okay. One thing that folks have talked to me about is sort of plans for next semester. So I've been pimping my classes right and left to try and get you excited about staying with us for statistics. A few of you have asked me if you thought that you could hack it next semester. Yes. Of course. The next semester's class, I think, is going to be an interesting blend of upper level students and beginning students. But the upper level students will have taken a different path to get there than what you guys are taking. And so I think that they will struggle in different ways than what you will struggle. But everybody is capable of doing it. So it's generalized linear models, repeated measures, and path analysis is what we're planning on covering next semester. And if you don't come, I won't be offended, but I will miss you. So it is called Applied Generalized Linear Models. It's listed as PSQF 7375. My plan, assuming I get enough people to support this plan, is to offer it every spring. And 6242 is going to be offered every fall. So I'm offering this class 6242 in the spring as well, because there's sort of a backlog of people who have put off taking statistics. Let's put that politely. And so we're hoping to sort of clear out the backlog, and then it will be predominantly entering students, I would expect, in the future. So. And if you ever have questions about what classes our department offers that would be useful for you in your research, given the kinds of data that you need to deal with and the kinds of places you want to work, I'd be happy to sit down and chat with you. My answer, of course, would be take everything because you can never know enough statistics, but I'm also realistic in knowing that you have a lot of other classes that are part of your schedule. So, all right. So any more homework questions before I shut this one down? All right, then bye-bye slopes. Bye-bye example 5. Hello, lecture 6. So we started this last time. We can do some review. Basically, up to this point, all of the terms that fixed slopes for predictors in the model have been sort of cooperative. They work together if there's more than one term to describe the effect of a single predictor. For each one, we'd want to know if it's individually significant. So that comes from the t-value, the univariate Wald test of estimate divided by standard error. We also want to know if they work together to capture a significant amount of variance in the outcome. The amount of variance that's been captured is known as what letter? The amount of variance that's been captured in an outcome by your predictors. R squared, yes. And it's squared because I said the word variance. So variance always implies something squared. And what letter gives us a test statistic for whether or not the fixed effects work together to get that R square? F, yes. So y hat, remember y hat? Predicted y from the fixed effects, from the slopes. R squared is the square of the correlation between y and y hat. Y hat can be determined by more than one slope. So everything up to this point has been sort of cooperative in nature. Now we're changing gears to talk about competitive. The idea of pitting predictors against each other to see whether or not they each retain their own unique effects after considering their redundancy. That's where we're headed here. And the example that I started with, the cast of This Is Us. We'll put them back up here. So my plea to watch the show, it's really good. It's on Tuesdays. Not that I've seen a live television show in probably 10 years. It's on Hulu, I should say. But we have the cast of This Is Us. So let's say we're taking an example from the younger Pearsons here, where they're approximately 11 years old. She gives them an assignment to clean the house. If 8 rooms or more are clean, the family gets a new TV, and each child gets a new Nintendo game for a unique room cleaned. So then we looked at each contribution here. She doesn't know who cleaned what, but this is what people claim. So Jack, the husband, claims he cleaned the master bedroom, the kitchen, and the dining area. Kevin and Kate both claim that they cleaned their own rooms plus the living room. So if this is all the information you had up to this point, how many Nintendo games does Jack get? He gets 3, right? Because he claimed 3 unique rooms. How many Nintendo games do Kevin and Kate each get? 1. Now what if we hadn't talked to Kate yet? We just talked to Kevin. He gets 2, right? So in terms of order, I think it was, Jeff, did you ask me about that, I think? Was it you? Maybe? Does order matter? While you're building your model, yeah. Because you don't know what's common until something else comes along that's in common. So yeah, if I just started with Jack, he'd get 3 rooms. If I added in Kevin, he'd get 2 rooms. But once I factor in Kate, Kevin's contribution has to go down because we don't know between Kevin and Kate who cleaned the living room. They can't both get credit for it. And then Randall shows up and he takes 2 of Jack's games away as well. So Jack's contribution, Kevin's contribution, and Kate's contribution look less when everybody's together in the model than when they're separate. So the question is, did someone clean the rooms, and then do they still get credit for the unique rooms claimed after we factor in the whole family? A lot of research questions are phrased that way because it's all about statistical control. If you can't control something experimentally, you try to control for it statistically, and this is the logic by which it happens. What's in common and what's unique. So it's expressed in terms of these Venn diagrams. Variance accounted for, variance in common. So if we have a predictor x1 here, The relationship in terms of x's overlap with y is both a and c. The relationship of x2 with y is both b and c. But c isn't common for both, so c isn't assigned in terms of contribution to either variable. But it still shows up in our square. It still contributes to the total amount of variance accounted for. Here's some math, in case you want to see that. If not, you can trust me. But the basic idea is that each predictor's contribution starts off with what it would be just bivariately, and then you have to subtract off the part that's in common. So in terms of vocabulary, we learned the term bivariate before, right? 2 variables. So if I put one predictor into a model, its contribution to the model I can say is its bivariate correlation. It's bivariate contribution because it's not controlling for anything else. We need a new word after we have more than one predictor in the model. And you would think it would be multivariate, but it's not. It could be multivariable, although not many people use that word. So I try to just keep it as either bivariate or unique. So bivariately, the relationship between x1 and y would be a and c. Uniquely, it's just a. There is a type of correlation that goes with this idea of unique. It's called semi-partial. A synonym for it is part, but the word partial is not the same. That is another kind of correlation that we don't need in our lives right now. So these map onto these areas if you square them, as shown. And you can get standardized versions or semi-partial correlations out of your model. They are very closely related. So this is to say that how you talk about effect size in these models is not just one thing. A lot of people use different things, and it can be confusing. So I wanted to show you how these things relate to each other, and then we'll see an example to where they overlap to most of the extent, but they're not exactly the same. But the key idea is that whenever you talk about a slope in a model where the 2 predictors or more are correlated, the word unique has to be in there. It's the unique effect of x1 after controlling for x2. Likewise, beta 2 is the unique effect of x2 after controlling for x1. It's this idea of what is not in common beyond the redundancy. Standard errors of these things also factor in the redundancy. So in the denominator, once you have more than one predictor in the model, is the unique variance of the predictor. So you can end up with higher standard errors to the extent that you have less unique variance. And so that is a problem that some people like to talk about. That's not really a problem. More on that later. So effect sizes for these things. Standardized slopes. You've seen this before, right? They're coming back. There's also another one that, to be honest, I didn't get taught when I was taking this stuff, but I've come to like it better. It's the squared semi-partial correlation. What it means in practice, it's the proportion, it's not proportion, let me say this correctly. It is the amount of the r square that variable is accountable for, responsible for. Not the proportion, but the amount. So if I have an r square of 10%, I might have a semi-partial squared correlation of 3% for x1 and 2% for x2, and I can say that x1 did more for my r square than x2 did. So I like this one in the sense that it's relative to a whole that you can understand. Standardized slopes are very common in regression. In terms of terminology, they are called betas in the output, whereas unstandardized slopes are sometimes called b's. Don't let that confuse you because in equations it's almost always written as betas. So that is to say you have to know what you're looking at in the software. They don't make it easy for you. It's not always the same across packages. So let me show you an example. Example 6. Yeah. We'll do this. New data set. GSS is gone. I know. So this is a data set that I made up. This is from my textbook. This is chapter 2 of that book. It's a book on longitudinal analysis, but chapter 2 is all about linear models because I found that folks often don't get taught the stuff about linear models that I need them to have for longitudinal models, so I put it in there. So these are fake data, but they're simulated based on existing real data, so they look like real data, in theory. These are older adults, 550 older adults. The outcome is a measure of crystallized intelligence known as the information test, so you can just think of it as cognition. We're predicting it from age, and note that age will end up centered at 85 years because that was near the mean of this sample. We're also predicting cognition from grip strength, which is commonly used as a proxy for physical health in older adults, for better or worse. It's in pounds per square inch that you can like squeeze on a little thingy. We have gender in here, which is coded as binary. In this case, men are going to be the reference group. And we also have a categorical predictor for dementia status. So these data are supposed to mimic the first occasion of a longitudinal study in which we know what happened with respect to a potential diagnosis of dementia for each participant. Some of them went the whole time never being diagnosed. Some people became diagnosed at some point during the study, and some people already were diagnosed at the beginning of the study. So none is the most prevalent as the group number 1. People eventually going to be diagnosed as 2, and current is 3. So we have 2 continuous predictors, age and grip strength. We have a binary predictor, and we have a categorical predictor, nominal in this case, more specifically. So what you guys know how to do up to this point is look at each of these in separate models. So that's what we're going to do to start with, not just for the sake of review, but also to be able to differentiate the reason for potential changes in the results later. So if I have a model in which I have both age and grip strength as predictors, let's say that age is not significant. Based on that one model with age and grip strength, I don't know if age is not related to cognition or it's not related anymore after controlling for grip strength. Say that again. If I have age and grip strength together in one model, and let's say age is not a significant predictor, I don't know if age was never going to be a significant predictor or if it's just not significant anymore after controlling for grip strength. To be able to differentiate those 2 possible reasons why age would be non-significant, I want to look at the bivariate relationships. So that's where we're going to start. Bivariate as a means of review, but also as a means of quantifying the extent to which each predictor is related to the outcome individually before combining them. Okay. Coding that you know how to do. So in SAS, I'm telling it where the data file is that I'm going to use. I'm opening up a rich text file to send my results to. I'm importing the data, which is already in SAS format. I also gave you a Stata version if you want to play along with these. So what do the first 2 lines here in SAS do that I have highlighted?
Allows to manipulate within the data set.
It tells us which data set to manipulate, and it does something else. So note that they're not the same.
You're saving it as something.
Save as, that's what we're doing here. So we're starting with from, is what set means. The one that's in file save, that's my permanent directory. That is within my subfolder right here. That's where my SAS file is. It's called this. I am taking that file that I want to keep safe and sound, I am making a copy of it and saving it in the work directory and calling it chapter 2. Now, do I have to do that? No. But this is the first time, I think, that I've started you off with a SAS file to go into SAS, as opposed to an Excel file or a Stata file or something else. The reason to do this is so that your original file stays safe and sound. Because there is no undo button. If you accidentally overwrite one of your variables, there's no like, do you wish to save before closing? Like, no, it happens instantaneously. It's gone. So please get in the habit of always immediately making a copy and working on the copy. Because it will be all too happy to write over your data and kill it. Are you properly scared now? Now, the same is not true in Stata. If you do modifications to a data set and you try to close the data set, it says, are you sure you want to leave without saving? And if you're happy with what you've done, you can hit save. If you're unhappy, you can say, yes, I want to leave without saving because I just ruined my data set, and all is well. There is no analog to that in SAS. SAS is hardcore.
Can you just, I know this is a little bit of extra work, but just make a copy file of your data set, one that you're working with and one that's just stored somewhere else so you don't mess with it?
You could do that. They can both be in the same permanent directory, but that would potentially lead to what I call file hell, where you have like 8 versions of the same file, all with slightly different names. Then you got to come back to and be like, which one did I actually work on?
Okay.
What happens with this is that the original stays safe and sound. At the end of your session, the temporary copy dies. Because you don't need it. Because once you save your syntax, all you got to do is run it again and you get back to the beginning of where you left off. So I tend to not save data sets, I just save syntax files. That's also useful if you have very large data sets where you, like a copy would take up physical space on your hard drive, but yeah. If you're super paranoid, it might be good just to keep a copy somewhere else anyway, like as, good record keeping, right, in the cloud somewhere or whatever. Okay, so we are save as a new copy in the work library. I'm making 2 predictors. How did I know to center at these points? Well, I ran proc means and got the numbers. So some of this is sort of iterative. I imported my data, looked at the descriptives, and then went back and made these decisions. But 85 is near the mean of the sample for age. 9 is near the mean of the sample for grip strength. Here's an example of else if then do in SAS. So I have dem group as the original variable that's coded 1, 2, 3. If dementia group is 1, here are my contrasts where N stands for none, F stands for future, and C stands for current. So NF to me means the difference between none and future, and C is the difference between none and current. So I'm creating both new variables set equal to 0 in this case. So that means that my dem group equals 1 is my reference. So given that I'm using else here, it's going to do this if it's 1 and then exit. So if dem group equals 1, it's going to do this step and then not even read these 2 lines. If it goes into it for a row of data and says, nope, it's not 1, keep going, oh, it's 2. I'm going to do this line and then exit. So if it's 2, then the first contrast picks up a 1. If it's 3, the second contrast picks up a 1 instead. And each of these do's has an end to go with it. Analog and Stata, gen the 2 variables equal to 0, and then systematically replace their values. I wrote it out long so that you could see all possible combinations, although some of these obviously are not necessary. But this gives you the logic a little more clearly. Okay.
So in this situation, we would use else.
Uh,
I mean, you kind of said that, not double.
you don't have to. It wouldn't create a problem to. if you have a very large data set that speeds processing to not have to do everything to every line. But if you're worried about screwing it up, don't else it. Just remove else from your vocabulary otherwise. So note I have a label here of a bunch of variables at once, and I have note semicolon is only at the end of all labels. So this is a common error that is hard to spot, but I've already troubleshooted at least once this semester. Let's say that I forgot that I was going to label all of these things, and I just put my semicolon here. Now what will happen? It'll yell at you, but it won't be clear what's wrong. So what SAS does, SAS is like Mr. Literal. SAS does not have a sense of humor. It'll say, okay, label age with this. Great, okay, I'm done labeling because you've shut off the word label. Now it's going to get down here, and it thinks you are trying to make a new variable, and what is to go into that new variable is words. That's what it's doing, because look up here. Grip equals this, it's the same. This equals words. And then it will go into the data set and say, wait, there's already a variable called grip, but it doesn't have words in it. I'm confused. I give up. Meh. That's my translation. Or Huey, when he got really angry when he was about 1.5, used to do this. That's SAS yelling at you. So yeah, it doesn't understand that you want to keep labeling. It thinks you're making a new variable and setting it equal to words. So only one semicolon at the very end. Otherwise, you have to keep saying the word label each time if you put a semicolon after each one. In Stata, there may be a way to do a group label, but I don't know how to do it. So I write it out every single time. And I've looked before and couldn't find it. So I give up. The only difference, no equal sign. In SAS, you have an equal sign before the label. Do you have to do these labels? No. Will someone yell at you someday if they get this data set from you and they're like, what the hell is grip 9? That's why. Data documentation, reproducibility, all that good stuff. That's why you need labels. To be honest, sometimes I put them in the syntax and don't actually run them because I don't want my output to have like tons and tons of words on it. But having them somewhere will help in the future people to be able to follow your work. So I am going to make copies of variables next to z-score for demonstrative purposes, because it turns out that you can get a standardized solution if you put z-score versions of the variables instead. So just to demonstrate that. And then last but not least, this. Have you seen this before? If you have, I've maybe done it once. This is an example of a function. nmiss is a built-in function in SAS. What it provides is the number of missing values across the variables listed as its arguments in the parentheses. So it's counting for each row the number of variables that are missing. And then it gets to the end and says, if that count for each row is greater than 0, delete. Now, why would I do that? Related to that, but no, I do that even if I weren't z-scoring. But yes, if I have missing data, then the z-scores won't be exactly mean 0, variance 1.
Because it's probably bad, but your study's dealing with old people and maybe they died.
I have seen data from dead people in data sets before, but this is not one of them.
Like they're still in the study at the beginning, but not anymore.
Well, this is so that would be true in longitudinal data, but this is one cross-sectional wave of data. So the reason that I'm doing this is because I have to, not because I want to. What I want to have is the sample stay the same across all the models that I'm going to run. Otherwise, I can't talk about change in R-square. I can't talk about change in coefficients because it's a different set of people each time. What's going to happen is if, say, somebody doesn't have dementia status, they will get kicked out of those models. So you would have sort of a moving window of a sample across analyses due to missing data. That is not desirable. However, kicking people out, also not desirable. So that's how to handle missing data is a more complicated topic. Basically, you have to be willing to make assumptions about why they're missing, and those assumptions are untestable. You just have to believe. Like in Santa Claus, or the Easter Bunny, or missing at random, as it were.
I don't understand if it was above 0 though, wouldn't that probably seem like there was data?
It's missingnesses that it's counting.
If the missingness of any of these is above,
If the number missing is above 0. So it's not counting if it's there, it's counting if it's not there. Yep.
Is this related to like almost guessed?
How are you thinking it would be? I don't think so, but maybe I'm wrong.
Is the cognition and aging, are those like predictors?
Cognition is an outcome.
Okay,
So in theory, it should be there all the time, and unless I have more than one outcome, in which case I want to.
that's what I'm thinking.
Yeah, so I'm just making it so that my sample stays the same across models. That's what I'm doing here.
So those are all.
Cognition is the outcome. These are my potential predictors. And so if I have somebody who has age, but they don't have grip strength, they'll be in the model that has age. They won't be in the model with grip. They won't be in the model with age and grip. They would be in the model with age and something else, right? And that's just a mess. So they get kicked out anyway, so it's good to pre-select. If you have a lot of missingness or missingness that's not random, so let's say that like people above 90 didn't get asked about their grip strength or something, that's a different problem that you would have to set up a different solution for. It's one of those special topics I was hoping we might get a chance to go over, but I'm not sure if we're going to. Because we're out of time yet again. But see, I caught it though. Aren't you proud of me, Gabby? I'm getting better at this. 1:45. I nailed it. And someone helpfully changed the clock. So, anyone else, children, get them up at like 6 a.m. because of daylight freaking savings time?
I want to go to bed at 7 p.m. That's
Oh, I know. Sunday was the longest day of my life, I swear to God. Like, how is it only 3 o'clock? I digress. All right, so I'll see you all on Thursday, office hours after class. Question?
I wonder if you have a cognition, you have a Z and the SAS node is a Z score.
Well, they're not z-scores yet. They're going to become z-scores down here. I just made a new copy so that it wouldn't overwrite the original variable. So I wanted both. Sure. All right, so office hours after my next class, 3:15, and I will see you later, Thursday. Done for real this time. Okay.